आवाज इको में आ रही है, मतलब मेरी आवाज मुझे ही रिपीट हो रही है, वहां से सुनाई दे रही है।
हेलो
जी देखो मेरी आवाज रिपीट हो रही है। मैंने रौनक वहां पे, इसका मतलब 2 डिवाइसेस ऑन है। Actually, Maruti Prasad ji, I was not speaking earlier. I was talking on phone. I just started my mic. Sorry. हाँ जी बताइए रौनक, अब मेरी आवाज आ रही है आप सब लोगों को वहां पे?
यस
वेरी गुड, नाउ इट इज ओके। तो मंडल जी अब आप ये आप अपना एक बार प्रेजेंटेशन काइंडली शेयर करके देख लीजिए वेदर इट इज वर्किंग वेल और नॉट, एंड यू आर एबल टू रीड थ्रू दिस स्मार्ट टीवी। वहां से दूर से वो नजर आ रहा है कि नहीं आ रहा है स्मार्ट बोर्ड से? अरे उनका अतुल जी, ये माथुर साहब का नंबर क्या है? आज तो मुझे लगा माथुर साहब के ऑफिस आए होंगे ना।
सर वो आज शायद ऑफिस आए होंगे सर, नंबर तो सर का है नहीं। मैंने दीक्षित सर से बात कर ली सर, वो ज्वाइन कर रहे हैं सर वो अभी।
वेरी गुड, अब माथुर साहब से मैं पूछ लेता हूँ एक मिनट है ना इंटरनली, इफ ही इज सिटिंग हियर। क्या नंबर है उनका? 207। यस सर, नाउ इट इज योर स्क्रीन इज शेयरिंग।
नहीं, फर्स्ट स्लाइड। फुल स्क्रीन। इज इट विजिबल?
अभी आपको केवल ना वही कंप्यूटर स्क्रीन दिखाई दे रहा है।
नाउ इज इट ओके? इज इट विजिबल?
अभी तक आया नहीं स्क्रीन।
हाँ दोबारा से। सेंटर में जाओ।
यस, नाउ इट इज ओके। Sir, now move the, yes, now it is moving. Next slide. Can you move on to the next slide?
हाँ just. Is it okay? Moving?
Not yet. ये स्क्रीन पे
आपको अभी कौन सा देख रहे हैं? फर्स्ट स्लाइड
सर, ये मेरे को आपका कैलिब्रेशन ऑफ वेट्स बाय सब डिवीजन मेथड वाला जो स्लाइड है आपके नाम से वो दिख रहा है।
फर्स्ट स्लाइड ओनली।
अभी भी ना आवाज मेरी वहां पे गूंज क्यों रही है? व्हाई इट इज इको? वेदर यू आर नॉट यूजिंग द दिस स्पीकर?
हाँ सर, स्पीकर की वजह से हो रहा है। सर को एक लैपटॉप दे देते हैं, उसमें इनकी मीटिंग चालू कर देते हैं तो फिर
हाँ, लेकिन अभी टिल द टाइम लैपटॉप से स्टार्ट करते हैं तब तक इसको चलने दीजिए।
ठीक है सर,
कंफ्यूजन नहीं होना चाहिए, उसको फटाफट करो। नाउ इट इज ओके, आई थिंक वॉइस इज क्लियर, एवरीथिंग। आई सर,
योर वॉइस इज क्लियर?
यस सर, माय वॉइस इज क्लियर।
यस यस। एम आई ऑडिबल?
Yes sir, you are very well audible. Now sir, kindly move your slides. I just want to see whether the slides are moving or not. Next slide. I am able to see your first slide only.
Just a minute. Is it okay? Moving? Is it changing now?
No, not yet.
Okay. Completely fresh open कर लेते हैं।
हाँ सर, वो लैपटॉप से कहाँ जी?
एक और फ्रेश प्रोफाइल ओपन कर लेते हैं या लैपटॉप कनेक्ट कर लेते हैं?
सर लैपटॉप से कनेक्ट कर देंगे तो इजी भी रहेगा आपके लिए।
Yes sir, now it is okay. I can see your second slide. Third slide. Sorry, not third.
This is a third one.
Yes, sir. I am able to see your third slide. Yes, it is first now.
But
Second.
problem is that in full screen mode it is not moving.
Sorry.
It is not in
Presentation
full
mode.
screen mode. It is not in
Presentation.
full screen mode.
Presentation mode. Ronak, why? Ronak.
Yes, sir.
In the left, there are two cross. One is for documentary recovery and the another is slides. Just make them cross.
Hey, 1 minute, sir. उसका रिमोट क्लोज कर दो, उसको कैंसिल कर दे, स्टॉप शेयरिंग कर दे, मीटिंग में जा पहले म्यूट।
आपका शेयरिंग हट गया।
1 मिनट हमने बंद किया, 1 मिनट।
मंडल साहब, ये जो बच्चे हैं, बेसिकली वी हैव द इंजीनियरिंग कॉलेजेस चिल्ड्रन ओवर देयर. These are 12 children who are doing this 4 months internship program at RRSL. 3 days back, they were in the last 3 days, they were in an industry to understand how they are manufacturing, what are the standards, how they are procuring the material, and how they are supplying in the international market. So they were learning about all these 3 things. My request would be today, you kindly let them explain how to do the calibration of even class weights using the subdivision method, and kindly explain them, not only explain them, hands-on training, how to calculate, get the uncertainty calculated. जो मेरे बच्चे हैं ये आसम वाले, इनको भी समझा दीजिए. No, I am not able to hear you, sir.
Okay, am I audible now? Am I audible now? Agarwal?
मंडल साहब बोलेंगे please? Now it is okay. Go move to the first slide.
Actually, in my presentation, I have added
First.
case studies also. Okay, some calculations of
लेकिन रौनक आवाज नहीं आ रही है साफ मंडल साहब की वहां से. जी सर.
Hello.
Yes. Go to the first slide. Yes. Thank you, sir. Thank you.
Yes. What I am saying is I have added case studies also in my presentation. See how to calculate the mass values as well as uncertainty using the subdivision method. So apart from this, if there is any further clarification or anything, definitely I am here to help. So
Thank you,
sir.
Thank you very much. ये रौनक ये स्क्रीन नजर आ रही है. यस, स्क्रीन आएंगे तो स्क्रीन पे केवल प्रेजेंटेशन आना चाहिए ना. आप दिखा रहे हैं तो फर्स्ट स्लाइड दिखाओ. फर्स्ट स्लाइड. Okay. Anyway, now we can start. Sir, my request is रौनक ये है, मेरा रिवाइज रिपीट क्यों हो रहा है?
सर आपका नेटवर्क स्लो है, आपकी आवाज भी ब्रेक हो रही है.
नेटवर्क भाई ये NIC का नेटवर्क है, ऑफिस में है, इससे फास्ट नहीं हो सकता. आपके नेटवर्क आपको मेरी आवाज आ रही है? रोने की रिपीट क्यों हो रही है आवाज? नहीं तो स्पीकर बंद करो और केवल टीवी को ऑन करो ना। स्पीकर बंद करके टीवी के स्पीकर को ऑन करो ना, सो दैट आपको केवल एक ही बार मेरी आवाज आए, रिपीट होके ना आए। समझ में आ रहा है? Yes, now it is not repeating. Now it is okay. Now it is good. Are you able to hear me? Are you able to hear me? Very good. Now I am also able to hear you what you are saying. So Mandal Sahab, first of all, good morning to all. Today we are having our workshop on a very interesting and important topic which is related with the calibration of even class weights using subdivision method. As in India, most of our laboratories, most of our experts are using ABBA method or ABA method. But this subdivision method, which is used for even class weights for calibration purpose, is a very important and somewhat complicated method. That's why we requested our Mr. Mandal from National Physical Laboratory to kindly have a lecture or a presentation how to calculate the even class weights or how to calibrate even class weights with the subdivision method and how to calculate the uncertainty. So I hope that this workshop will be very useful for all those laboratories, all the legal metrology officers who are working in the states and our regional reference standards laboratories, how to calculate the even class weight. Sir, with your kind permission, we will put your presentation and video on this YouTube channel and presentation in the groups so that the participants can be benefited even after the presentation, if with your kind permission. Thank you. Thank you, sir. Sir, secondly, sir, my request will be, as we have these 12 children available at this laboratory, you kindly explain them hands-on training how to find the uncertainty, how to calculate the uncertainty of these even class weights using subdivision method during the afternoon. I will be there in the RSL because I'm in office. There is some meeting, and after this meeting, I'll come to Ahmedabad in the evening today, and then tomorrow we will meet and we'll discuss what they have learned during the last week and what they have learned in the industry where they went and the projects whatsoever we have requested them to prepare the reports, whether they have prepared or not. So tomorrow I will discuss with all these, and today evening I will be in the office. Sunil ji, and जो भी office का काम हो वो मेरी टेबल पर रख देना, so that when I'll come I'll do that. So now I would like to welcome all the participants. We have with us our Shri B.N. Dikshit Sahab. Sir, you are available? Are you able to hear me?
Yes, yes.
Thank you, sir. Sir, this is a workshop on even class weights. I would like to request you to kindly inaugurate this workshop, please.
Yes, yes. Very nice to uh, that this program is going on in RSL Ahmedabad, and there is a lot of peoples are there who are participating in this very program, and we are finding that it is on even class accuracy of weights. So that is one of the highest accuracy class of the weights, and this required the lot of techniques for the measurements. So we required the balances, we required the laboratory conditions and fixed temperatures, and there should not be dust and all those type of things, and manpower should be also trained जो है. So those things is required जो है. I feel that RSL Ahmedabad is taking such initiative, such a great initiative. So I feel very happy to integrate these very programs. I hope that it will be very good for the industry as well as for the engineering college as well as for the laboratories who are doing this very work. Thank you, Agarwal Sahab, and all the participants.
Thank you very much, sir. Thank you very much for your kind words. Sir, now as we have with us Dr. Mandal, everybody in India knows him. Not only in India, he is an international expert in mass. We are privileged to have with Mr. Mandal today with us. I hope that in India, I think there will be nobody after Mr. Tripurari Lal, as unfortunately he is not with us now. I think he is the next man after Mr. Tripailal, and he has learned a lot from Tripailal Saab. So it is our privilege to be with you, sir. Kindly enlighten us and let us know how to calculate this uncertainty, please, sir. Now over to you, sir.
Thank you, Agarwal sir. Good morning to all of you. Good morning, PN Dixit sir, former director, and our Dr. Venugopal sir, Director CSR NGL for giving me permission, and thanks to Agarwal sir for organizing this national workshop regularly. Is organizing for the national cause, and I am happy to be part of this support. And in this stage, this is my third lecture. First one was on going balance. Second one was on the substitution method, and this is about the subdivision method. So these are the various methods, and definitely balance and weight. These are five methods. For the balance calibration, we need the standard weight with the desired accuracy, and for the calibration of weight, we need suitable balance. So today we cover the substitution method. So I will try my level best to explain as easy as possible, because the subdivision method is really a very complex method. Earlier it was used at the NMI level only. So I will try my level best. So thank you very much. So without taking much more time, just I would like to continue. And thanks all the participants, those who are online, and all the students, those who are there. So because just I was interacting before this program, as they were mentioning in their syllabus during the curriculum, there was no measurement of this thing. So I think in future we think about that to improve measurement uncertainties of. So I would like to start. Agarwal sir.
Please, sir, please.
Yeah. So today's topic is calibration of weight by subdivision method. So what is subdivision method? I will explain after two slides. So myself, Gautam Mandal, Senior Principal Scientist at CSR National Physical Laboratory. CSR National Physical Laboratory is designated as National Metrology Institute. Now first we should know what is metrology. Metrology is science of measurement and its application. This is basically science of measurement and its application. So we can divide metrology in three categories. One is scientific metrology, industrial metrology, and the legal metrology. Scientific metrology, this is for the maintenance of standard maintenance, upgradation, all these things. And industrial is a direct application for the manufacturing. And legal metrology, we are at this moment I am in the RSL Ahmedabad. Those who are responsible for maintaining of the standard legal metrology for the legal metrology, there are 5 RSL, and I will cover all these things in my lecture. So metrology, even for the taking legal action, if this is the responsibility of the legal metrology to ensure that what consumer is paying, they should get the right quality. If they are not getting, then they have right to take action to legal metrology department. But before taking any legal action, we should ensure that this measurement is correct. Suppose if I pay 1 kg of weight, I should get 1 kg of weight. But if I am being cheated, first you have to ensure that this with 1 kg weight was used, and nowadays electronic balances are commonly used instead of weight. Even balance are giving the correct result. And there should be some permissible limit, because 1 kg may not be exactly 1 kg. There should be some permissible limit. If it is within the permissible limit, then acceptability. If beyond the limit, then they can take the action. So this is the responsibility of the Department of Legal Metrology. Legal inspectors are there regularly, they verify all this. So these are not the calibration, these are called verification. So today although I will not cover about the verification, we are going to the calibration. And scientific metrology and the industrial metrology, this is according to ISO IC 17025 to the quality system. We maintain the quality system, and the quality system, there are various requirements for the standard. These are technical requirements, management requirements. So these are, so CSR has both the responsibilities to maintain the standard for legal metrology as well as for the scientific metrology. Earlier, as we know, there are various measurement systems. Are used CGS system, MKS system, FPS system. But currently, we are following SI system. It's the international system of units. According to SI system, there are 7 base units: second, kilogram, mole, candela, Kelvin, ampere, and meter. So there are 7 SI base units, and all other units are called derived units. All these derived units are derived to this base unit, and these are the concepts. These are already defined. These standards are defined to this constant, like for the kilogram. Now these are defined to the Planck constant, and this is a fixed value defined by the CGPM. What is CGPM? I am coming after this slide. So CGPM has fixed this value 6.626 070 minus 34 June 2nd. So like that, there are 7 base units, and for all the 7 base units, there are fixed value of physical constant, and all the units are defined to physical constant now. Although today I will discuss about the kilogram, and it has been redefined. Has been effective from 20th May 2019. These are few standard weights. Actually, this concept of weight or mass is nothing new. This has been using till human civilization. So from this photograph you can see, so there are various weights, but only thing is that time there was no uniform measurement system. Various different units are used, various sales, various materials. So there is no uniformity. So it is good within the small community, but for the import export of the things, it is quite difficult. So that's why we need some uniform measurement system. So first time during the French Revolution, during the 1793, first time this was the uniform measurement system was adopted. That initially mass of the kilogram was defined as for the mass of the 1 liter of weight at 0 degree Celsius temperature was the kilogram. But after a couple of years, it was redefined further 0 degree Celsius to 4 degree Celsius, because at 4 degree Celsius, density of water is maximum. But at the same time, problem is that property of water is different, and this varies with location. So, and also it is not transferable. It is not easy to transfer from one location to other location because of liquid state. So that's why the same year in 1795 it was converted to brass artifact. So that was the first kilogram was made in artifact form. So that's why it is called provisional kilogram. But at the same time, brass is not very stable material. It's a soft material. So that's why, but when we say this is our standard, this will be stable with time. So that's why in 1799 it was converted into platinum. So platinum was used because platinum is noble metal, the less corrosive material. So stability is very good with time. So history, there was meter convention was signed in 1875 among the 17 countries for the uniform measurement system. So that time 17 countries signed this meter convention, and BIPM was established in France. And 1879, this platinum weight was further redefined. It was material was used 90% platinum and 10% iridium, because platinum is, although it is a noble metal, but at the same time platinum is soft metal. So that's why to increase the hardness, 10% iridium was used. So 1879, when this order was given to one London company, Johnson and State prepared around 40 national port type kilograms. And next one was recognized as international port type of the kilogram. And first time in 1889, it was mentioned as international port type of the kilogram. So that time defined.
I'm sorry, sir.
Yeah.
Sir, na, I think request. Clearance of voice.
My voice is not clear.
Now it is clear.
Okay.
Sir, my request is you kindly put the mic somewhat farther from your mouth and try to speak. Please.
Now it is okay.
Yes, sir.
Yes, sir. Okay. So in 1889, that time is it okay now?
Yes, sir.
Yes, sir. Okay, thank you. So that time definition of the kilogram was kilogram is the unit of mass, and it is equal to the mass of the international port type of the kilogram. So whatever mass of this artifact was considered as 1 kilogram, and that is the main drawback in this case, because there was no option to measure this artifact. So after just cleaning and washing using the BIPM method, it was assumed as 1 kilogram. So that's why, as this is the graph, so with time it has been noticed that international port type kilogram has changed by 50 micrograms. Although there is no direct method to measure it, it is an indirect method. So that's why further it has been redefined. Now it is linked to Planck constant. Now we can measure the international port type kilogram also. Now this is the definition of the kilogram, which is effective from 20th May 2019. The kilogram symbol kg is the SI unit of mass. It is defined by taking the fixed numerical value of the Planck constant T to 6.626 07015 into 10 to the minus 34, were expressed in the unit joule second, which is equal to the kg meter square per second, where the meter as a second had already defined in terms of speed of light and frequency of cesium 133. So this is already defined. Now kilogram is defined to meter and the second. So actually, purpose of this slide is to show. So this is a continuous process. So redefinition is a continuous process. Although quantity is same, actually before redefinition there was various hype in the news channel, newspaper. If quantity has changed, quantity has not changed. 1 kilogram is 1 kilogram. Only measurement technique has changed. So this is a continuous process according to the technology available in the world in the present scenario. Even during the 1879, when it was first time sanctioned as IPK, that time it was decided 1 kilogram plus or minus 1 milligram will be considered prototype. So nowadays we are talking about the microgram level. So technology has been advanced at that level. We are talking about the micro level. And that time, even for the international port type kilogram, it was decided that it should be plus or minus 1 milligram only, according to technology available at that time. And this is a slide actually, as I said, meter convention was signed in 1875 among the 17 countries, and India signed this Meter Convention in 1967 and became member of it. There is a CGPM. CGPM is the General Conference of Weights and Measures, and this meeting is held at BIPM every 4 years among the directors of Metrology Institute. After that, CIPM is their international committee for weights and measures. Their duty is to monitor the activities of the BIPM. BIPM is the laboratory, International Bureau of Weights and Measures. After that, there is joint committee of RMOs, the Regional Metrology Organization and the BIPM. So there are various committees there, and there worldwide there are 6 RMOs. We are under APMP because broadly this RMOs are based on the continent, and there are 12 technical committees. Every year we meet during the November and December and discuss various international activities going on, advancement of these things. As NPL, National Physical Laboratory of India, or CSI National Physical Laboratory, is as NMI will represent all these international bodies. So purpose of to include this slide is that actually frequently we receive various queries from our customers, stakeholders about the if CSR and flexibility of the CSR NPL is valid or not, if CSR NPL is NABL accredited or not, if they are any CMCs, if they are following the quality system or not. So various queries we frequently receive. So that's why I have intentionally added this. Actually, I have a paper published in Maman jointly with our quality manager and our former director as well. So we included this. See how this complete system, how we can get uniform measurement system established and followed. As I said, there are 6 RMO, Regional Metrology Organization. So we are under APMP, Specific Metrology Program. Also, we go to the peer review. Like in case of NML accretion is concerned, this is through the accretion body. This NML is the national accretion body for testing and calibration laboratories in India as of now. It's the national body, and NMI will go through the peer review to the of their respective RMO. Once this peer review is held, their report is circulated among other RMOs as well as intra-RMO. This is called intra-RMO and the inter-RMO. When all the RMOs accepted our PMC, then only this is published in BIPM KCDB. KCDB is the key comparison database. So those who are interested to know the PMCs of the NMI can visit the BIPM KCDB site and take the PMCs, their parameters and their values. And this is actually flowchart of CMC entries. I am not going all this detail because this is just difference from the accreditation body that when one laboratory applies for the accreditation officer appoints assessor from the according to this field. Those are independent assessors of the in this field they appoint. But in this case, NMI can select the expert, but condition is that the expert should be from the other NMI. So as CMC better than that NMI or at least equal. So there are various committees, as I mentioned, there are 12 committees. One committee is for technical committee for quality system, this is common for all. But there are various technical committees as also for mass and related quantities, this is PPM. So we can NMI can request to respective PC biodata of the assessor for this peer reviewer. Then they can approve. And fortunately, I got opportunity to visit Sri Lanka for the peer review. And this report will be, I have submitted this report to PPFF because this was on the volume, and this liquid volume is under PPFF, Technical Committee for So this will be circulated among all the RMOs and also inter-RMO. So when all the RMOs will accept CSC, and there is various procedures, CSC will be reviewed by independent reviewers, those who are not involved in the peer review process. So after that, there is through a PhD secretary and CCRG. Finally, there are 20 states, and finally it is published in DIP KCDB. So purpose of this slide is to show that this is a very complex system, and it takes around 2 to 3 years and sometimes more than that to publish one PMC in DIP and KCDB. And coming back to marks. So marks, as we know, marks is a very important parameter, and it has applications in our day-to-day life, either from the satellite launching to pharmaceutical industries or purchasing of jewelry to normal grain and vegetable everywhere. So that's why we should know this quantity very accurately. Apart from this application, other few derived parameters are also depending on the mass. So this is our photographs of the kilogram. We got this copy after becoming member in 1957. We got this copy. This is copy number 57. This is a unique number in the world. So made of platinum iridium, 9% platinum and 10% iridium. So all these derived parameters are traceable to this kilogram. So like volume, density, pressure, force, fluid flow, the CRM certified reference material, or in Hindi, the Bharatiya Interceptor BAD or gas metrology. So various derived parameters are also depending on the mass. So that's why you should know this mass quantity very accurately according to desired accuracy. So these are the various symbols used in mass metrology related to mass quantity. Sometimes people used to use capital K, capital G, or capital K, small g. So these are wrong symbols. These are green. These are the correct symbol. This should be small letter of small k, small g for gram, small g, like that. Just on unit, those are named after any renowned scientist. Then only this unit are used as capital letter. Otherwise, these are all in small letter of. Like Newton is named after Isaac Newton. So that's why it's a Newton. But there is one exceptional in case of liter. We can use both small and capital L. Reason is that if we write one L, small letter, sometimes it looks like 11. So it may create some confusion. To eliminate this confusion, international community has accepted both small letter as well as capital letter. So this is not named after any renowned scientist. So this is the very important. This is the metrological traceability because this is the heart of the measurement. So what is the definition of the metrological traceability? So this is the property of the measurement result, whereby the result can be related to a reference to a documented unbroken chain of calibration, each contributing to the measurement uncertainty. So this is basically the property of measurement result, and it should be unbroken chain, and all are having the measurement uncertainty, and this all should bring back to SI unit. So when we report the result, measurement result is measurement value plus or minus uncertainty. Although K factor may vary according to degree of freedom, but usually there is an international practice it is taken as K equal to 2, and all the CSCs are considered as K equal to 2. So SI based unit is maintained usually at PIPM, or not all the cases. Few cases is at NMI level and through the intercompetencies are established. But in case of mass, the case SI unit maintained at PIPM today. And after that, the NMI in our case is the NPA line. Our international code is NPA line, the international national Physical Laboratory of India, because there is another NPL in UK. So to distinguish two organizations, we use the NPL line, National Physical Laboratory of India. And after that, accredited this testing and calibration services provided by the accredited laboratories, the manufacturer, then final product which are launched in the market. So every year uncertainty will increase. Not necessarily it will be 10 times. Just I have shown for the indicated purpose only. So purpose meaning is that down the line our uncertainty will increase because uncertainty of standard is already included in the calculation of the uncertainty of that stage. So that's why it is shown in pyramid because down the line it will increase. This is a hierarchy of mass standard traceability. So this is the before redefinition of the kilogram. That time kilogram was defined to the mass of the international prototype of the kilogram. It was assumed as kilogram as I have mentioned. After that, Dy.Dir has reference standard. There are 6 reference standards, and these working standards are basically used to check the stability of the international prototype kilogram time to time. Although it has been used only 3 times in last 130 years, this international prototype of the kilogram. And these working standards, there are 3 working standards. These are used to calibrate the national prototype of the kilogram. In India, this is a unique number in the world, the copy number 57. All these weights are made of same material, that is 90% platinum and 10% iridium. After that, in NPL, there are transfer standards because we can, since this is a this international prototype kilogram is the highest in the world, it's the senior in the world, IPK. And this national prototype of the kilogram NPK is highest in our country, and it is kept at CSIR because Government of India has given responsibility to National Physical Laboratory to maintain the standard through Weights and Measures Act. It was effective in 1956 first time. After that, time to time it has been revised in 1976, then 1988, and currently this current edition is 2009. And this the Weights and Measures Act 2009 and subsequent national standard rules, Government of India has given the responsibility to maintain standard. So that's why it is kept at NPM, and every 10 years it is sent to BIPM for the recalibration. And since it is the national prototype kilogram and it is single piece in our country, so this is a private standard, national standard, so it is not possible to use for the regular purpose. So that's why we have 4 transfer standards, 2 made of nickel chromium and 2 made of stainless steel. And purpose of this selection of this material is that it is not possible to use the platinum weight everywhere because platinum is very expensive material. Even sometimes its cost is more than gold also. So it is not possible to use everywhere. So that's why next substitute material is the stainless steel. Because at the same time we have to select the material such a way that the stability should be maintained with time. Stability, their fining, the roughness, all these things. So that's why stainless steel is used. And nickel chromium is used because we provide a traceability to the Department of Legal Metrology also. Although nowadays Legal Metrology Department is using the stainless steel weight, but earlier they used to follow the adamant bronze weight, and density was 8,400 kg per cubic meter. So also the density of the nickel chromium is close to 8,400 kg per cubic meter. To eliminate the air moisture correction, we have selected this material. After that, we have, these are only 1 kilogram, but only 1 kilogram is not sufficient to fulfill all our requirements, our day-to-day life. So that's why we are international kilogram.
कैमरा वही है ना?
May I continue?
हाँ, please.
So this is the traceability before redefinition of the kilogram. Now redefining the kilogram.
Oh, thank God. It is very good now.
I can be measured using the Planck constant. Now only change is that earlier IPK was assumed as 1 kilogram with zero uncertainty. It was assumed as exactly without any uncertainty. Now uncertainty has increased to 20 microgram after redefinition. And accordingly, this NPK, transport standard, all this answer, all the levels has been revised. Even BIPM has also redefined published CMCs this time, and also they have decided every 2 years intercomparison will be held, and accordingly they will revise the CMCs of all the NMIs. Initially, our CMC was 28 microgram at 1 kg, but at present this is 49 microgram. It has increased to 49 microgram as of now. So rest other things are same, although it has not affected the CMCs of any accredited laboratories, because even for the E1 class, CSR NPL provides 160 microgram per E1 class. So it is very much higher than our CMCs. So this is well with our reported uncertainty. That's why we did not call back any certificate for the reissue. So these are already accepted. Now this is although we are well aware about this difference between mass and the weight, because from our school days we know this mass is basically quantity of matter in that body. And there are two types of masses. One is the gravitational mass. This is a universal law of gravitation, or inertial mass, and Newton's law of motion. But for the practical purpose, because here we are discussing about the practical purpose, for the practical purpose, both are same. And the weight, this is the attraction force towards the center of the earth. But whenever metrology is concerned, mass means there's a true mass. True mass is only used to distinguish between mass and the conventional mass. Conventional mass means weight. Okay? So mass means, if we use the word only mass, that means this is the true mass. So, and the conventional mass means weight. And what is the difference between true mass and the conventional mass? Suppose if we take weight of a body, if we put this body on the weighing pan, it will apply some force, that is mass into gravity. So basically when we do the calibration means this is a comparison between two weights. One is the standard weight, whose value is previously known, we have certificate, and test weight means whose value is unknown. So this is a comparison between two weights. So both the independent weights are putting, if we put on the weighing pan, it will apply some force. So for the test weight, Ft, the force of the test weight is mt, the mass of the test weight multiplied by local g, gravity, acceleration due to gravity. Same thing for the reference weight. But this is applicable in the vacuum. Vacuum means there is no air. But only problem is that mass is used everywhere, and it is practically not possible to create the vacuum, isn't it? If we go to market to purchase something, even if it is gold, silver, or any product, it is not possible to create the vacuum. Or in other way, if we are able to measure this air density very accurately, and till date it is not possible to measure the air density directly. It is calculated using the mathematical equation, either it is CIPM formula or the approximation formula. And it is also not practically possible. Okay. So that's why usually this comparison are carried out. When this comparison is carried out in air, one upthrust is applied according to Archimedes principle. And this is equal to the volume of that body multiplied by air density into G. And so this is applicable for both the weights, test weight as well as reference weight. In comparison in air means test weight minus reference weight. So just replacing all these terms, finally we get mt, mass of the test weight, equal to mass of the reference weight, which is taken from the certificate, then volume of the test weight, this is mass divided by density of that weight. Vr is the volume of the reference weight, again mass divided by volume of that density of that weight, and rho is the density of air, and delta m is the difference between test weight and the standard weight, which is calculated using the balance. But as I have said, it is really difficult to measure the air density everywhere. So that's why international community has adopted a new concept that is called conventional mass. Conventional mass means if we consider the air density 1.2 kg per cubic meter, this is at sea level, and how much deviation is there from the reference air density. We have to apply that much air density only. So we can eliminate. So earlier, suppose in case of Delhi is concerned, their air density is around 1.15 kg per cubic meter. So it will be multiplied by 1.15. But in case of conventional mass, it will be multiplied by 1.15 minus 1.2, that is multiplied by 0.05 only. It will be almost negligible. And also if lab is located near the sea level, suppose in Chennai or Mumbai, where air density is very close to 1.2, so we can eliminate the air buoyancy correction. So in that case, we can compare any material. So we can eliminate the air buoyancy correction. So for practical purpose, usually we commonly use this conventional mass. So all the classification are based on conventional mass only. But for the international prototype kilogram, national prototype kilogram, these are based on true mass, because we need the accurate mass. Even in case of international prototype kilogram, if it is 1 microgram less than the nominal value, we cannot say this is a 1 kilogram. Every time during the application, we use 999.6 times 9 kilogram. But in this case, when we go to market or visit the jewelry shop for purchasing gold, never jeweler says this weight is 500 milligram plus or minus this much. They say this is a 500 milligram. So if it is within the permissible limit, we can consider as nominal value. So this is the purpose. So there are 9 accuracy classes: E1, E2, F1, F2, and M1, M12, M2, M23, and M3. There are 9 accuracy classes according to applications. And all these accuracy classes are based on conventional mass only. So this is the basic difference, mass and the conventional mass. So that's why I have put the true word in bracket. If only mass word is used, that means this is mass or true mass. Or conventional mass means weight. If we go through the standard YML at 111, it talk about the conventional mass or weight. But true mass is used when we have to realize the standard. But for the commercial purpose or any application, we use the conventional mass. So there are two methods for the measurement of mass. One is the substitution method, other is the subdivision method. Substitution method is one-to-one comparison. Means in this case, we should have two weights of same nominal values. 50 kg against 50 kg, 100 gram against 100 gram, 1 kg against 1 kg. And as a standard, we can use the combination of standard weights also. Although this combination of standard is not used for the, although there is no restriction in the standard, but it is not a good practice to follow this combination of weights for the lower nominal values like milligram weight or gram weight. For example, to calibrate the 50 gram weight, it is not good practice to use the 20 gram plus 20 gram plus 10 gram, because multiple weights create some problem for the eccentricity error of the balance. So it is applicable for the higher nominal values. Another method is the subdivision method. Subdivision method means one reference weight can be used to calibrate different other nominal values. Those are not same nominal value. Here we should have of same nominal value, but there are different nominal values. 500 gram, 200 gram, 100 gram. Reason is that BIPM has given us only one weight, that is 1 kilogram. To derive from 1 kilogram to other nominal value, to establish other nominal values, we are bound to follow this method only. There is no choice. We have to follow subdivision method only. We cannot follow the substitution method, because we cannot compare 1 kg against 1 milligram or 1 kg against 1 gram. Although earlier I have already discussed about the substitution method, so directly in this lecture I have included subdivision method. So this as I have mentioned, this BIPM has given only 1 kg weight, but for our application purpose, there are other nominal values are required. We required milligram weights. For example, in case of pharmaceutical applications, they need milligram weights. And even in gram, milligram, kilogram, even in few tons also for transportation, all these things. But it is not possible to compare 1 kg against 20 kg, 1 kg against 1 milligram. So that's why one special method used, that is called subdivision method. Means we have to divide. Those nominal values are higher than the 1 kilogram. Those are called multiple weights, multiple of 1 kilogram. And submultiples means those are lower than 1 kilogram. So these are the decade. Decade means we have to make a series 500 gram, 200 gram, and 100 gram. This is compared against 1 kilogram, because 1 kilogram is our base unit. After that, when this 500 gram, 200 gram, and 100 gram, this series is established using 100 weights, will be used as standard for next decade to establish 50 gram, 20 gram, and 10 gram. And for the next decade, one of the 10 gram weights will be used standard, then 5 gram, 2 gram, 1 gram, like that. Likewise, we can go up to 1 milligram. So there should be some weighing reason, and same thing we can applicable for the higher nominal values or multiple weights also. So when we receive the weight, say set of weights, usually it is very commonly receive the weights from 1 milligram to 200 gram of E1 class weight. So in this, there are 200 gram weights and 100 gram weight. But to complete the series, we need other nominal values also. For example, in case of substitution method, if only one weight, that is 500 gram. We can compare against our 500 gram standard weight and issue a certificate. But here, even customers submit the single weight, we have to complete whole series. So what to do? We have to use other weights from our standard. These are called check standard, because this mass values of these weights are already known, but we include in this series because this is a very complex method. There is matrices are there. If mass values of these weights are okay, okay means these are already known. Now, after completion of the measurement, if we are getting the mass value within the acceptable limit, then we can say whole series is okay or acceptable. Okay, now, and this dot, this is red and green, this is only for the identification purpose. I don't know it is visible or not. Here it is, dot is used only for the identification purpose. This is 200 and 200 dot. So that's why I have put in a red dot and the green dot for the identification purpose only. Now, this series is completed. Now we can start the measurement. To follow, so that's why to follow this method, always we should have all the weights of that series. So this is our weighing design. There are 12 combinations, different combination. So first 500 gram plus 200 gram plus 200 dot and 100 dot. See, this is basically for the identification purpose only up to 200 gram weights. So combination of 1 kilogram. So here also nominal value should be same in that series. So combination of 1 kg should be compared against single 1 kg. And this one, this is our A1. And next time we have to replace 100 dot with this 100 with 100 dot, and again we have to repeat. Then after that it is not possible to make 1 kilogram because this combination is not possible. This is a maximum. So next time 500 gram against 200 gram plus 200 gram plus 100 gram. So 500 gram single weight against combination of 500 gram. So likewise, there are 12 combination, and we can see, so first 4, this is a unique. After that, A5, A6, this is a common in that sense. This is a repetition actually of same weighing design. The 7, 8, 9, 10, 11, 12. These are repeated twice. So what is the reason? I will explain later on. Why this in this weighing design this combination has been repeated. But to follow this weighing design or this method, this combination should be same. We cannot change any combination. So this is a combination of 1 kilogram. So all the weights we have to put, not one by one, all the weights at a time we have to put on the weighing balance, and we have to take the reading. We have to note down the reading. And after that, we have to put 1 kilogram. After stabilization, we have to note down it. And what is the difference between combination of 1 kilogram minus standard weight? So this is our A1, first difference. Next time, just we have to replace 100 gram weight with 100 dot. Now we have to repeat it. Combination of 1 kilogram against 1 kilogram. So here combination of weights and the single weights, so nominal value should be same. Reason is that to eliminate or minimize the linearity error which is followed for the substitution method. Concept is same. Only thing is that in this case we use combination of weights. So again 1 kilogram. Then this is E2. A2. So I am not repeating all this. So similar fashion, first we have to take 500 gram weight, and after that combination of this 500 gram. So minus means if we put bracket here, it will be 200 gram plus 200 gram plus 100 gram. So we have to complete all this 12 combination. after that, this matrix is formed. So A, this one A is the coefficient of used in this weighing design multiplied by is the unknown, and this is the our balance difference. Actually, in this case, it is put here S plus A1 and S plus A2. After that, we have not used standard. So that's why A3, A4 is a alone. So S plus A1, S plus A2, after that A3, A4, A5 is like that. And this is multiplied by A transpose. Then after that, we solve it. What is it? We can see that in this column, this is first 4, this is 1, 1, 1, 1 means plus 1, and after that 0, 0, 0. Here, this coefficient is 1 and this is applicable for 500 gram. So 500 gram weight was used for this first 4 combinations only. So that's why this is a 1, 1, 1, 1. And rest is a 0. So this is for 500 gram. This is for next column. This is for 200 gram. After that, the 200 dot, then 100 and 100 dot. After that, 1, plus 1, plus 1, minus 1, minus 1, then 6 times 1, 1, 1, then 0, 0. So this is a plus 1, this minus 1, minus 1, and after that, this is a 6 times plus 1, then 0, 0, because we have not used 200 gram in this combination. So like that, we have to use the coefficient. So that's why I have said we cannot change this combination. If we change the combination, entire equation will be changed and all the measurement will go wrong. So we cannot change any equation, any combination, any symbol of any sign also. Because what I am saying, showing here, this applicable for this particular weighing design. If you change the combination, then you have to recalculate according to your sign. So this is basically 5 by 12 matrix, and this transpose is row will be column and column will be row. Then it will be multiplied here. Now we have to multiply. This is a multiplication of matrix. So 1 into 1, 1 plus 1 plus 1, this is a 4, then 0, 0, 0. So after normalizing this equation, we can get this 4 here. So those who are interested to calculate, so can do the calculation only for your practice. So I'm not going all these calculations. So basically purpose as in this weighing design, repetition of the weighing design was that to get the diagonal matrix only, because all other elements are 0. So very simple equation. Otherwise, worldwide there is various other subdivision methods, and in that case, sometime even earlier in NPL also we followed various other weighing design, not this one. That was various complex calculation. So this is very easy. So only we can get the diagonal matrix. So that's why there are repetition of the combination. So now we can calculate 4 into 500 equal to this one. So 500 equal to half of this. So this is basically 500 gram is half of the 1 kilogram. Okay, so our standard is 1 kilogram. So half of this, and 1/4 of A1. A1 is the small capital A1 equal to small a1 plus small a2 plus small a3 plus small a4. These are the values we got from this weighing design, and 500 gram weight was used only for these 4 combinations. So that's why here I am trying my level best to explain as easy as possible. Otherwise, there are various mathematical calculations are there. So A1 is applicable for 500 gram, A2 for 200 gram. So all are in sequence. 200, the A3 for 200 dot, A4 for 100 gram, and A5 for 100 dot. So all are in sequence. So for this is 500 gram was used only for the first 4 combinations. So that's why A1, A2, A3, A4. After that, A2, A1 plus A2, then A3 minus A4, then A5 to A10, this all are plus. Here, this is plus, so that's why A1 plus, A2 plus, A3 minus, because minus sign is there. So coefficient is -1, then minus A4, then after that A5, A6, A0 up to A10, this is all are plus. But 200 gram was not used in this combination, A11, A12. So that's why it is not here. So like that, we can calculate. So these are directly related to the weighing design. So that's why if you change the combination, so your sequence should be same. If you change the combination, entire measurement design will change and your final result will go wrong. So 500 gram equal to half of the standard plus 1/4 of A1. Then for 200 gram, 1/5 of standard, then 1/10, because 10 times we have used here. There's a 10 coefficient, then A2, then A3, again 10 combination, 10 coefficient. Okay. So these are interrelated.
So how this 1/2 of S is coming or 1/5 of S?
This one?
Yes, sir.
This one actually 4 into 500 equal to 2S plus A1. Okay. So 500 gram will be 2 by 4, that means half S, and 1 by 4 A1. And next time 100 gram, 10 into 200 equal to 2S plus A2. So it will be 2 by 10 means 1/5 plus 1 by 10 A2. So similar way you can calculate the other nominal values also. So this is the solution of the weighing design, how to get or how to establish the other nominal values using the single reference standard weight. And after that, for the next weighing series, just we can use 100 gram as a standard. Then we can establish other nominal values, 50 gram, 20 gram, and 10 gram. Just I am showing one case study. So before starting the measurement, we have to note down the environmental condition, because as per standard YML R111, YML is the International Organization of Legal Metrology. It's a free document. Those who are not aware about that can download from the website. It's a YML R111. It's a free document. So this is the temperature, RH, relative humidity, and the pressure are monitored during the measurement. And as per standard, temperature should be 0.3 degrees Celsius per hour, and RH should be 5% in 4 hours. So that's why every hour we monitor temperature to know if variation is within our acceptable criteria as prescribed by the standard. So that's why we monitor every hour we monitor temperature, RH, and the pressure. And this is the uncorrected value. After that we apply the correction, because all the instrument used for the calibration, either it's a thermometer, hygrometer, or the barometer, get calibrated from the respective standard group of CSR NPL, and we apply the corrections. And this is the air density equation. Equation is given here. This is called approximation formula. Most accurate formula is the CIPM formula, CIPM 2007 formula. This is also given in the YML R111 standard. And this is the most complex equation. It is not required to use that equation used when prototype is used, because prototype is basically made of platinum iridium, and volume is approximately 46 cubic centimeter. And next level, if we use the stainless steel weight, density is around 8,000 kg per cubic meter, and volume is 125 cubic centimeter. So volume difference around 79 or 80 cubic centimeter multiplied by air density, because in that case we use the true mass first. So volume difference multiplied by air density, if you multiplied 80 multiplied by 1.15, you can calculate around 93 to 95 milligram air buoyancy correction we have to apply. So if temperature variation is even more than 0.1 degrees Celsius, it creates a huge change, where we are talking about the only 49 microgram of uncertainty. So that's why that time we use the approximation, that time we use the CIPM formula, which one is the most accurate formula. But even in for the E1 class, we can use the approximation formula. Also, I published one paper comparison among various air density equations. There are 4 or 5 various equations. Those are used worldwide and compared against CIPM formula. And this variation was within the 0.01%. So we can easily use, which will not affect in our measurement, even in case of E1 class weights. And after that, here we have used 3 different combination of weights, because our standard was, although this is stainless steel weight, all are stainless steel weights, but density of the weights are different. So that's why even in case of E1 class weights, we have to apply the air buoyancy correction. So this is the volume of 1 kg weight of the transfer standard. Then we have used check standard. Their density was different, the volume was different. We can see the volume of transfer standard was 127 cubic centimeter. For check standard, approximately 124 cubic centimeter, and the test weight, this is 124 or 125.99 to approximately 125. So we have to apply air buoyancy correction. So here we have calculated the air buoyancy correction for each combination between transfer standard and the check standard, transfer standard and the test weight, and the check standard and the test weight. So there are 3 combinations are there. So we have to calculate volume difference multiplied by air density during the measurement multiplied by reference air density, that is 1.2 kg per cubic meter. So we can calculate the air buoyancy correction. Now in this case, 1 kg is standard, 200 gram, 200 dot and 100 gram are the test weight which are received from the customer, and the 500 gram and the 100 gram, these are the check standard. So this is our combination according to weighing design. So combination of all the weights are put in the weighing pan. So we are tear the balance. So that's why it is 0, 0, 0. After that, when you put the 1 kg weight, it is the difference between this combination of weights minus this weight. Then again we have repeated this 1 kg, and A means this is the combination of weight. So here, usually in case of substitution method, we calculate B minus A, test minus standard. But here this is not concept about standard or test, because here we are using only one standard. This is about the combination. So here should be A minus B, because this is according to weighing design. And according to this weighing design, combination of weight minus standard. So we have to calculate this minus this. So that's why this is 6 points. So earlier it was in gram, now this is a milligram. So this is multiplied by 1000. So unit is very important here. Now after that we have to use apply the air buoyancy correction. So because in this combination 500 gram was our check standard, and combination of 500 gram was test weight. So this compared against transfer standard, whose density was something different. So here 50% of this combination between check standard and the transfer weight, and 50% of test weight and the transfer standard. So we have to calculate air buoyancy correction. We have to take it from here, 50% of this value and 50% of this value as summation of this. So this combination is very important. So what I am showing here, this is applicable for this particular combination only. If combination changes, then all the calculation will change. So that's why basic concept should be same, not the numerical value. Basic concept should be same, because as I have already mentioned, if customers submit only one weight, and if we use 4 check standard from our own, then density will be different, volume will be different, and air buoyancy correction will be different. So in that case, we have to calculate that way. So I will show some other case study also. So that's why this is the 50% applicable between check standard and the transfer weight, and 50% between transfer standard and the test weight. So this is a combination of weight. So similarly, next combination, we have to apply the air buoyancy correction according to our combination. With here 500 gram and 100 dot. This is our check standard. So we have here will be 60%, 40%, because 200 plus 200 is the test weight. So here 60% between check standard and the test weight, and 40% between test weight and the transfer standard. So accordingly, we have to apply the air buoyancy correction. So this is all the observed value I have shown here. This is a combination, and after applying air buoyancy correction, this is the difference plus air buoyancy correction. So this is our this is a 12 combination, A1 to A12. And after that, putting the data A1, A2, A3, A4, we can calculate the A1. Similarly, we can calculate the A2, A3. Just we have to pick the data according to this combination, A1 or A2 or A3, A4. And at the same time, we have to keep in mind the sign also, plus sign or minus sign. I am repeating again and again, if you change the sign or if you change the sequence, entire measurement will go wrong. So that's why concept should be clear. And after that, this is a 500 gram equal to this equation already I have shown, the half of the 1 kg plus 1 by 4 A1. So we have to use this, and we can get this is our value. For 500 gram, this is for 200 gram, 200 dot, 100 and 100 dot. So using the single weight, single standard weight, we can determine 5 unknown. And out of this 5 unknown, although this used 500 gram and 100 dot as a check standard, because these values are already known. Now we can compare from earlier value and this value. If it is within the acceptable criteria means if it is within the reported uncertainty, then we can say yes, entire measurement is correct. If something is wrong, that means we have to repeat whole measurement process. So one part is over, as I have mentioned. He measured this reported result means measured value plus or minus uncertainty. So this is our measured value. One part is over. Now we have to calculate the uncertainty. This is unlike substitution method. In case of substitution method, what we do, we calculate the deviation from the mean. Suppose if we take the 6 observation, then calculate the mean, then how much deviation is there from the mean. But here, different combinations are there. These are not single nominal value. So what to do? We have to calculate other way. So once these values are known, we have to put this value, this calculated value, in that equation, weighing design. Okay? 500 gram, we have to put in that 500 gram, instead of nominal value, we have to put the measured value. 500 gram, 200 gram, 200 gram, 100 gram, minus 1 kg. So theoretically, we should get the same result, because we have derived this value using that weighing design. If we go back, theoretically, we should get the same result. And that's why you have to check if we are getting the same result or not. Okay. So now
this value is this. So accordingly, we can calculate this 12 observed value. Calculated value. Then we have to calculate the residual error. Residual error means, as I have mentioned, theoretically it should be the same value. So we have to calculate the deviation from observed value and the calculated value. How much deviation is there? This is called residual error. In case of substitution method, what we do, we calculate the deviation from the mean. And here we calculate the observed deviation from the observed value. Observed value minus calculated value. So this is the value. So we have to calculate the square of this value, then summation, sum of square of all this value divided by degree of freedom. In this case, not n minus 1, because here unknown are 5. So n is the number of observation, this is 12, and k is the number of unknown, that is 5. So summation of this square term of all this residual error divided by 7, we can get the standard deviation. So this is the standard deviation. Now we have to calculate the type A uncertainty, or due to weighing process for independent weight. So for the 500 gram, this is half of this standard deviation. Half is coming from this weighing design. As we know, this type A uncertainty is coming from the statistical data. So here statistical data is applicable for second term. So it will be 1 by 4 square. Whole square means 1 by 16 multiplied by the number of coefficient. So there are 4. So multiplied by 4. So 1 by 4. The square root of this is half. It is not half of the standard weight. So that's why it is half. And for other 4 nominal values, all the cases, these are 1 by 10. That means 1 by 10 whole square will be 1 by 100 multiplied by all the cases, these are 10 coefficient. So 1 square plus 1 square, this uncertainty always calculated in square term. So that's why here minus 1 square will be plus. So multiplied by 10. So 1 by 10 and square root of this is the 1 by root 1 by root 10 multiplied by standard deviation. So for 200 gram and 100 gram, this is the single value. For 500 gram, this is the value. So this is a type A uncertainty, or due to weighing process. So this is the only component under weighing process or type A uncertainty. Then type B. Since this is a standard uncertainty in the reference weight itself was 49 microgram divided by, always when we calculate the uncertainty, we calculate the standard uncertainty, because 49 is the expanded uncertainty. Expanded uncertainty divided by coverage factor. The coverage factor is k equal to 2. So all the uncertainty should be converted into k equal to 1. Because in the certificate, maybe 1.96, maybe 2.03, maybe 2.28, or any other value. So we cannot combine all these values. So that's why first we have to convert our uncertainty into k equal to 1. That is called standard uncertainty. Standard uncertainty means k equal to 1. So this is our standard uncertainty, but this is applicable for 1 kilogram. Because this is, we use the standard of 1 kilogram. So this is for the 1 kilogram. So for 500 gram, it will be half of this from this equation, because half of the standard, because uncertainty was associated with this value. So this is a half of this value, 1/5, then 1/10. So half of this value, this is our value, 1/5, then 1/10. So independently we can calculate the uncertainty due to reference weight used or reference standard used. Although I have not shown here the drift of the standard, otherwise we should calculate the drift also of the standard. Drift means this is called instability. Instability means this is the deviation from previous value. Theoretically, it should be same. As we say, mass is always constant. But for the practical purpose, it is not same. It is changes with time. So how much deviation is there? This deviation, suppose this weight was calibrated 3 years ago, and there is deviation is 3 microgram. So this 3 microgram is called instability or drift. So this much value we have to incorporate in the uncertainty calculation. So although I have not shown here, so you have to calculate drift divided by root 3. This is a rectangular distribution. And this is the most complex component, that is air buoyancy correction. So that's why to follow the subdivision method, one should aware about the substitution method also. So this is the standard equation to calculate the uncertainty in air density. So UF is the uncertainty in equation itself, which approximation formula was used. So this is 0.302 into air density. In case of CIPM formula, it is used at 301. Here it is 302. This is double the CIPM formula. And UP is the uncertainty in barometer, which was used for pressure measurement, and P is the pressure, mean pressure monitored during the measurement. UT is the temperature during the measurement. This is uncertainty of the thermometer. P is the mean value, and URH is the uncertainty hygrometer, which was used for monitoring RH. And since it's a relative term, that's why this is 100 square. So that's why it is 10 to the power 4. This one, this one, this one. URH is the uncertainty in hygrometer, which instrument was used to monitor the RH during the measurement, divided by, since is the relative value. Always we say this is 30% humidity or 80% humidity. So this is a relative term. How much moisture is there in air? So this is in terms of 100 actually. So that's why this is 100 square. 100 means already 10 square, and square of it is 10 to the power 4. Now this is the 3 parameters we monitor during the measurement: temperature, RH, and the pressure. And this is the standard deviation, because every hour we measured the temperature. So how much standard deviation is there? Standard deviation divided by root n. This is our type A uncertainty. Here also we follow the same combination, type A and the type B. Type A is coming from the statistical data, that is monitoring during the measurement, and type B, it is the uncertainty taken from the certificate of the respective instrument. So this is the expanded uncertainty reported in the certificate of that thermometer divided by coverage factor. This is the standard uncertainty. Then US square plus UV square, then square root of our whole. It is our combined standard uncertainty. This combined standard uncertainty for the temperature, this is used in this equation in case of UT. Similarly, for the RH, for the relative humidity, it is the standard deviation of RH divided by root n, because in that equation actually we had taken 4 observations. So that's why standard deviation divided by root n, and this is our type A uncertainty. So similar way you can calculate the combined uncertainty, and this combined uncertainty used in this equation to calculate the So this is the type A uncertainty. Type B, sorry, I missed one thing. This is the type B uncertainty. The type A uncertainty, it is the standard deviation among the, just I would like to go back. Just, this is the air density, the standard deviation of this air density divided by root n. This is our type A uncertainty in air density. This is our type A uncertainty divided by root n. This is our type A uncertainty in air density, and this is a type B uncertainty air density. After putting all this value, we can get the type B uncertainty. Then after that, we have to calculate the combined uncertainty of air density. So this is the uncertainty in air density, combination of type A uncertainty and type B uncertainty. Yes, you are asking about the UF. UF is the uncertainty in formula itself. This one. So this is a formula in itself. So this is the uncertainty air density. Now we have to calculate the uncertainty in air buoyancy correction. So since there were 3 different combinations between transfer standard and the stick standard, transfer standard and test weight. The air buoyancy correction for that individual weight, 500 gram, 200 gram, and the 100 gram. Then we have to calculate accordingly. This, for example, 500 gram. We use this 500 combination between 500 gram and the 1 kg was applicable only for the first 2 combinations, because we used 1 kg weight for the first 2 combinations only. So that's why it is coming 1 by 16 means 1 by 4 whole square multiplied by 2, that is 1 by 8 and square root of this. So that's why if we change the combination of weights of different materials, all this equation will change. So what I am showing here, this is applicable for this particular combination of weights only. So every time we have to use the air buoyancy correction, we have to calculate the air buoyancy correction accordingly. And this is the uncertainty due to display resolution. This is d divided by 2 root 3 multiplied by root 2. Root 2 is coming from the 2 weights. 2 weights means one is the combination of weights, other is the standard single weight. So that's why 2 times we have used. So after simplifying this, d divided by root 6. So this is our value. After that, this is a combined standard uncertainty. So we have to calculate the combined standard uncertainty for independent weight. For 500 gram, just I would like to go back here. For the 500, sorry. For the 500 gram, we have to take this value for the type A uncertainty. Then this is due to reference weight. This one is due to air buoyancy correction, and this one is due to display resolution of the balance. So we can calculate the uncertainty in 500 gram. So similar way, we can calculate the uncertainty for 200 gram. There's the same for 200 and 200 dot. But there is a difference between 100 and 100 dot, because this 100 gram is the test weight and this one is the check weight, check standard. So that's why air buoyancy correction is slightly different. Here it is 0.34, here it is 0.32. Although final value is same, because other components are dominating in this case. So this is our combined standard uncertainty. Then we can calculate the effective degree of freedom using the formula. This is the same as substitution method, then accordingly we have to select the coverage factor. I have taken from the YMLR 111 standard according to this effective degree of freedom, then combine standard uncertainty multiplied by coverage factor. This is our expanded uncertainty. So here we have to calculate the expanded uncertainty independently for each weight, 500 gram, 200 gram, 200 dot. Since there is the same value, that's why I have clubbed here. Then 100 gram and 100 dot is different, so that's why I have shown here different way. So this second part is also over. This is our reported uncertainty. As per the requirement of the standard, this is the uncertainty budget. Although this is something different from the substitution method. This is not the standard table is used for the substitution method, because in that case actually we show only one unknown weight, but here we are showing the 5 unknown weights. So that's why just I have modified this uncertainty budget accordingly to accommodate all the values. So to show all the calculations here in this tabular form. So this is our final reported value. And this is our final result for each weight. For 500 gram, this is our measured value plus or minus uncertainty. For 200 gram, 200 dot, 100 and 100 dot. So this is our 5 unknown weights. We can determine the mass values of 5 unknown weights using the single reference standard weight. For this is the first series is completed. After that, for the next series or decade, we have to use any one of the 100 gram as a standard for the next series for 50 gram, 20 gram and the 10 gram. So just I am showing another case study that is little bit this simple calculation compared to earlier one. Reason is that, but it is applicable only we received the weight from 1 milligram to 10 kg. And in that case, what we did, 1 kg was compared against our 1 kg following the substitution method. Okay. Once 1 kg is established, then that 1 kg was used as a standard for this 500 gram, 200 gram. So all these weights were taken from the same weight box. So assuming that all the materials are same, densities are same. So that's why, but in this case also one check standard was used, that is 100 gram from our side. Because in the box, usually manufacturers use the 500 gram, 200 grams and 100 gram. But to complete the series, we need another 100 gram. So that 100 gram was used as check standard. So that's why little bit simple calculation is there. Just I am showing what I am showing here, just to show the calculation, how much deviation is there from earlier calculation to this calculation. So all these things is also variable. So depending on the case-to-case basis. So this is the same way, just we have to monitor the environmental condition every hour. Then after that, we have calculated the air density using the same equation I have not shown here. Then combination, this air buoyancy correction between check standard and the test weight. And after that, this is the same table we have used. Only thing is that here, weighing design also same. Only 500 gram, 200 gram, 200 dot and 100 gram. These are of all the test weight are same box, and even 1 kg reference weight also from the same box, because earlier we have measured 1 kg against standard 1 kg. Now it is known. Now only 100 gram check standard was used in this case. So in first case, combination of 1 kg was compared against 1 kg. So here all the test weight are of same material, made of same material of the manufacturer. So assuming that these are materials are same, so density is same and volume is same. So there is no buoyancy correction was applied. So that's why it's 0. But here we have used the check standard. So we have to apply the air buoyancy correction for 100 gram only. Okay. Here we have calculated air buoyancy correction for 1 kilogram. So 1 kilogram divided by 10, because we are taking for the 100 gram only. So 1/10 of 1 kg. So that's why it is taken as 0.007, 7 microgram only. So accordingly, we have to calculate the air buoyancy correction. Here it is plus, because this according to this check standard minus reference standard, but here combination is just opposite. Here test weight minus check standard. So that's why sign has changed. So it is also keep in mind, because here we have calculated test weight minus check standard. So here it is minus. Since here combination is check standard minus reference weight or test weight, so that's why it is plus, here it is minus. Just trying to show that every time it will change according to our combination and according to our application, difference, material difference. So all these combinations are same. Here we have to complete the 12 observations for every cases. Then after putting the this observation, we can calculate the A1, A2, A3, A4 and A5. Then again we have to calculate this our reference standard weight, mass value of reference standard weight used, and after that this for the A1, then A2, A3, and we can calculate the mass value of independent weight used in this combination. So similar way, but only thing is that air buoyancy corrections are different in this case. So little bit simplified compared to first case. And again we have to calculate this concept is same. Just we have to put this observed value, calculated value in this weighing design. Then we have to calculate the this calculated difference, and we have to calculate the residual error, this observed value minus calculated value. Then again we have to calculate the standard deviation. Here it is same in case of type uncertainty is concerned. Only difference is applicable in case of air buoyancy correction. Here air buoyancy correction, because it was applicable only for the 100 gram, so it is calculated accordingly. So it is not applicable for the other nominal values, because material of the 1 kg and material of the 500 gram was same for the same manufacturer. And after that, this is the uncertainty due to display resolution of the balance. Then we have to combine all this component we have calculated. So for the 500 gram, same fashion we have to calculate independently, 500 gram, 200 gram, then 100 gram. Then we have to calculate this effective degree of freedom and the final expanded uncertainty. And this is the uncertainty budget. So similar way we have to calculate the all the calculations. So only difference was here air buoyancy correction. And this is the final result in this case. Now just I am showing the next weighing design, how to calculate one. This first decade of series is completed. Now 100 gram is used as a standard. So same weight design, only thing is that instead of 500 gram, it will be 50 gram, then 20 gram, 20 dot, 10. Then all the weighing design is the same. We have to follow the same thing. Only nominal values are same. And just combination, same thing you have to follow. And again, we have to repeat. We have to interchange first these weights, then we have to make the combination. So I'm not showing any numerical value in this case. This is because all these calculations are same. Now, once measurements are over, now for the classification purpose, to give the compliance, it is meeting the requirements of the E1 class or not. How to do? So there is two requirements of the standard. One is expanded uncertainty should be 1/3 of the maximum permissible error. That is MP. Delta M is the maximum permissible error. And maximum permissible error minus uncertainty, this is called error. So this error plus or minus, this should be within the conventional value of that particular nominal value. So basically, it's already available in standard. Well, R111 standard, I have taken from the standard only. So these are the 9 accuracy classes: E1, E2, F1, F2, M1, M12, M2, M23, and M3. These are various accuracy classes. So E1 is the highest accuracy class. Then E2 is the second highest. So these are classified according to applications. Suppose for the normal grain and vegetable, no need any applications on micro level. So in that case, that even milligram is sufficient according to nominal values also. Similarly, for the pharmaceutical industries, in that case, we need the uncertainty in microgram level. Yeah, error in microgram level. So in that case, usually use the E1 class weight or E2 class weight. So these are various applications are there. So all these are classified according to the applications. So usually E1 class is traceable, directly traceable to the prototype as per the definition. So now I am showing how to classify. For example, 1 kg. For the 1 kg, 0.5 is the delta M. Delta M means maximum permissible error. So it should not be vary more than 0.5 milligram in 1 kg. So uncertainty should be 1/3 of 0.15, 0.5. That means 0.16. Uncertainty should be 0.16. This is a maximum limit. It may be less than that, but not more than 0.16 milligram. So uncertainty should be 1/3 according to this criteria, first criteria. Okay. Next time, error is MP minus expanded uncertainty, means 0.5 minus 0.16, that is 0.34. So error should not be more than 0.34. So that means 0.34 plus 0.16 equal to 0.5. So error plus uncertainty equal to MP. So this is not that sometime I have seen during the assessment of the NABL assessment, laboratory just check this 0.5 in case of E1 class or whatever accuracy class is there. Just simply they consider the maximum permissible error of that accuracy class and that nominal value. This is not the case. It should be 1/3 of that MP, and error should be MP minus expanded uncertainty. That means this uncertainty plus error should not be more than MP. So in this case, for 1 kg, uncertainty should not be more than 0.16 mg and error should not be more than 0.34 mg. Now just I am showing one graphical example I would like to show in this. So this is our maximum error limit. This is a 0.5. Just I am showing the upper limit only. It is applicable for the lower limit also. I am showing the upper side only. So 0.5 and uncertainty is 0.16, maximum uncertainty. That means our error is 0.34. So if measured value lies accordingly, for example, green one, this is clear pass, including uncertainty, it is well within our acceptable criteria. Red one, last one, this is clear fail. Even including uncertainty is beyond the permissible limit. So this is a clear fail. But problem is that about this purple color and the blue color. These are called conditional pass or conditional fail, because few part value is within the permissible limit, acceptable limit, but uncertainty is the beyond the limit, partially, not completely. Here, value beyond the permissible limit, but with uncertainty, it is partially within the limit. These are called conditional pass or conditional fail. But as far as YML or triple one standard is concerned, both are fail. That means, as per ISO 17025, those are attending from the enable accredited labs, or those are applicant of the enable accredited labs, or for the any accredited bodies. So please, those who are following the YML or triple one standard, according to this standard, these two cases are clearly failed. And as standard define the risk factor, so here risk is covered in the standard itself, because standard has given the clear-cut guidelines what is the criteria for the classification to provide the compliance. So in this case, risk is already covered in the standard. So decision rule we can take accordingly the standard has provided, which is given in the YMLR 111 standard. So in this case, only this one is pass, green one, and all three are considered as fail. But one thing is there, as 17025, this is a risk-based thinking is applicable in this standard. If laboratory considered this, reduce this uncertainty, for example, this is 50% is beyond this limit. It is maximum limit is 0.16 milligram. They can consider as 0.08, say. So it will be considered as within this acceptable criteria if they can reduce this uncertainty. But at the same time, we have to consider the validity period also. Validity, if we are giving the 2 years validity, 3 years validity, with this uncertainty 0.16, is it applicable the same validity for 50% of uncertainty of this? If we are reducing the uncertainty 0.08, is it acceptable for 2 years also? So we have to think about. So that's why you have to consider that risk-based thinking is there according to the standard. So that's why in NPL usually we don't provide lesser uncertainty. Always we provide the maximum one. Although we have capability to provide the best uncertainty, but we don't provide due to this reason, because we provide 3 years validity also. And so this is the criteria for the upper limit, and in case of lower limit, it should be 999 point, then 3 times 9, 66. So 1 kg minus 0.34. So same thing is applicable for lower side also. So thank you very much. So thank you very much for kind attention. So hope I am able to explain. I have tried my level best. I don't know I am able to explain or not all these things. So thank you very much.
So can we take online queries?
Please.
In the chat box, you can see, sir.
Even help. Initial disturbance.
Yes, sir. From here, sir.
In the weighing design, which denomination of the weight is under calibration? Actually, this is depending on this. This question is that in this weighing design, which denomination of weight is under calibration? This is in this case, actually, for example, I have shown in case of decade 1, this all the 500 gram, 200 gram, and the 100 gram are the test weight. Only 1 kg is the reference weight. Some of the manufacturer of SS mass weight don't follow the making method as prescribed on YML at 111. Page 13. Nominal value of.
So, shall I read out loudly? Some of the manufacturer of SS mass weights don't follow marking methods as prescribed on OEML R111. Page number 20-22, like nominal value to be written in top of weights from 1 gram plus weights distinguished by dot or star on F1 weights, nominal value followed by F, on F2 weights, nominal value followed by gram per kg on M1 class weights, and no marking on all E class weights, and 1 mg to 500 mg weights, as mg weights are identified by shape and distinguished by star or dot in case of 2 mg, 20 mg and 200 mg. Please explain.
And if actually definitely manufacturer should follow the requirements of the standard. If they are not following, suppose during the receiving of the weight for the calibration, so I don't know you are from the calibration laboratory or not. In that case, you can reject it also. And if it is bring in your notice, you can bring to our notice also. So we'll because this is case to case basis. Without evidence, I should not comment. So if it is in your notice, just provide the evidence. So accordingly, we can follow the action.
Next question is how to calculate drift of weight.
Drift of weight, actually, this is standard is calibrated. Suppose 2 years ago or 3 years ago or 1 year ago. So how much deviation is there? Suppose this same standard weight was calibrated in 2020 and again in 2022. So how much deviation is there? This is our drift. Or in standard, it is terminology is used instability. So this is the same thing.
Okay. The next question is why we not calibrate non-standard weights that are not specified in this MP table like 1.5 kg, 2.5 kg, 4.5 kg, etc.
Actually, yes, we can calibrate using the same method. YML standard does not restrict for the standard nominal value. Only consider this condition is that we cannot provide the compliance, because this compliance are based on the standard nominal value in the order of 1, 2, and 5. If you go through the nominal value, here you can see this slide is still open. This 20 gram, 50 gram, 100 gram. Then 200 gram, 500 gram, then 1 kg, 2 kg, 5 kg in the order of 1, 2, and 5. So that's why in the box, usually it is used 1 kg single weight, then 2 kg, 2 weights, then 5 kg, 1 weight, like that to complete whole series. So in that case, for example, if non-standard in case of Newton weights for the force metrology, because force is derived parameter of mass, so definitely we have to the traceable to mass metrology only. So in that case, for example, in case of 100 Newton, so 100 Newton divided by G value, if we consider 9.79 meter per second square, it is usually 10.214 kg. So in that case, we have to use the combination of weight, 10 kg plus 2 kg, 10 kg plus 200 gram plus 10 gram plus 2 gram, like that. We have to use, even in milligram range also, if we have to minimize the linearity error. But in this case, only thing is that we cannot provide the compliance, because these are equivalent to F1 class or F2 class or any other accuracy class. These are not exactly F1 class, because this design, this is a disc weight, these are not according to YML R111 standard. First one. Sometimes these are construction like adjustment cavity, all these things are not meeting the requirements of the standard. So we cannot provide the compliance actually. We cannot, we can use the same method which is used for the, this is usually follow the substitution method, but we can provide the compliance.
Okay, the next question is, sir, why give uncertainty 1/3 MP? Any reason?
This is actually standard requirements. Actually, usually this is taken as 1/3, because error plus uncertainty should not be more than MP. So this that means 1/3 is uncertainty, 2/3 is a error.
Another one is on the same question.
This already.
Okay. Can you please enlighten on the Appendix D of YML R111 regarding check standard? This person is asking about check standard, sir.
No, can you elaborate on the Appendix D of YML? Okay, you can send me mail. Actually, right now I don't have this standard actually. So you can send me mail. My email ID is Gautam, Goutam, @nplindia.org. Just I repeat, GOUTAM @nplindia.org. You can send me mail, so I will definitely get back to you, and I'll be happy to help you.
The next question is, sir, when do we use subdivision method? And do we need to consider the magnetic parameters?
We have to, yes, we have to consider all these things.
Uncertainty is defined specific to balance resolution only as commented by NAB assessors. Like balance resolution of 1 mg, uncertainty is in 3 digit. But when we follow 1/3 scenario, sometimes we need to go for 4 to 5 digit in expanded uncertainty. Can we do beyond the balance resolution?
No, we cannot report beyond the resolution of the balance. Suppose, for example, if balance resolution is 4 decimal place, so you can report up to 4 decimal place only. You can reduce the decimal places. You can reduce to 3 decimal places or 2 decimal places, but not 5 decimal places. And at the same time, you have to keep in mind uncertainty and the value should be up to same decimal place. And first we have to decide the decimal place of uncertainty, suppose up to 3 decimal place, and according to you have to round off your measured value. It should be up to same decimal place only.
Next is how to do intermediate check of weights of even class.
How to do intermediate? Actually, definitely is a very tough sometime, because usually in the laboratory they use only one weight box. So either you can compare just there are two weights, 200 gram or 200 grams. You can compare between 200 gram or 220 gram, or just time to, although direct weighing is not reliable, but since you are using the this E1 class weights are used with the control environmental condition, so just time to time you can take the direct reading and calculate the air buoyancy correction. Not air buoyancy correction using these differences. Actually, it is a 1 minus rho A by rho S. Rho is the density of, yeah. Then regularly you can monitor. So if there is any deviation, so likewise you can calculate it.
The last question is when we select subdivision method over substitution method.
When we select subdivision method over substitution. Okay. Actually, for all the accuracy classes, even for the E1 class also, you can follow the substitution method, but usually it is standard. Also, there is no restriction. You can follow 120 if it is meeting the requirements of the standard. But sometimes there's a restrictions in the resolution of the balance. It is not possible to achieve that much uncertainty or error using the substitution method. So that's why you follow the subdivision method. First of all, in case of NMI is concerned, it is the mandatory, because in NPL, BIPM has already I have mentioned, in NPL, BIPM has provided only 1 kg to the each NMI, including NPLI. So we have only 1 kg. So we don't have any choice. We have to follow this subdivision method only to establish other nominal values. But in case of other accredited laboratories are concerned, if it is meeting the requirements of the standard, because in case of E1 class also we can follow the E1 class, because as of now, according to the standard YMLR 111 standard, E1 class is the highest accuracy class. So we can compare as per standard. We have to use one order higher accuracy class standard, because to calibrate the E2 class we should use E1 class. For F1 class we have to use E2 class, 1 class higher standard. But only exception is that in case of E1 class we can use the E1 class to calibrate the E1 class. But sometimes problem is that using the E1 class it is not possible to achieve the E1 class following the substitution method. So that time we have to follow the subdivision method.
Any questions from your side?
So hope I am able to address all these queries, or even in future if there is any queries, so please feel free to contact me through my email, or you can directly contact to Ashutosh sir. So he will contact to me. So I will be happy to help. Thank you very much.
Thank you,
Thanks,
sir.
sir.
Thank you.
Thank you.
It's a great session, and Yeah. Sir, can you please write down your mail ID here so that they can contact you?
अग्रवाल सर नहीं आ रहे अभी, अग्रवाल तो दूसरी जगह पे हैं। उनको बोलना पड़ेगा अतुल जी को। एक मिनट, वो माइक ऑन करके बोल दीजिए कि वो करना। माइक ऑन बोल दीजिए ना कि वो फोटो लीजिए फोटो।
Yes, sir.
पोस्ट का ऑप्शन
So, after entering
अच्छा।
the
अच्छा ऑटोमेटिकली
हेलो, हाँ समझ बोला तो उसमें
so there around 186 166
86 victims. 86.
86
86 है ना? मेरा भी विजिबिलिटी 170 कहाँ देखा आपने? ऊपर, अच्छा ऊपर की 5 भी ऐड कर ली, वो तो अपन नहीं 5 नहीं, ऊपर
नहीं ये ए है
यहाँ
अटेंडेंस
ये 165
165
165 168 हो गया।
मैम तो दे आर लिविंग
Please be on. Please kindly switch on your videos.
वो तो वहाँ से
On. पर बोलना तो पड़ेगा, ये लोग जा रहे हैं। All the attendees, please switch on your videos. We will be having some screenshots. It is requested to please switch on your videos. वहाँ से ले लेंगे ना?
सबका शायद आएगा नहीं, सबका देखने में आएगा नहीं
नहीं आएगा, नहीं आता। Picture search रहेगा।
चालीस लोग
उनसे फोन करके
Over.
पूछना कितना टाइम, फिर लॉग आउट करते हैं।
5 मिनट 5 मिनट तो सबको कैरेक्ट करने में लगेंगे, फिर उसके स्क्रीनशॉट खींच लेगा वो कॉपी नहीं, वो वहीं से बुक करते हैं। 43 लोगों को बना दिया।
Hello. Thank you.
Thank you, sir.
Thank you for nice presentation.
गुड आफ्टरनून दीक्षित सर
Yes, sir. Yes.
गुड आफ्टरनून सर
Good afternoon.
एम आई ऑडिबल
Yes. It was very good presentation,
हमारा नहीं होता तो
and people are more interested in balances and weight and so many issues are there, sir. Because it is used in most of the industries. No? So uh, they are talking for the intermediate balances and weights. That should be also calibrated. Thank you, sir.
Thank you, sir, for giving opportunity.
Thank you.
Thank you so much, sir. Thank you
Thank
so
you
much.
for coming.
Hello,
Thank
sir.
you all the
Mandal sir,
participants.
hello. Hello. How are you? How are you? Hello, sir.
Hello.
सर आप लोगों से निवेदन है कि आप लोग अपने कैमरा को ऑन कर लीजिए सर। एक स्क्रीनशॉट लेना है आप लोगों का। जितने भी लोग पैनलिस्ट बन चुके हैं वो सब अपने कैमरा को ऑन कर ले सर। अभिजीत कुमार, अफजल, अमित कुमार, अमित यादव, आनंद कुमार पाल, आप लोगों से रिक्वेस्ट है कि आप अपने कैमरे को ऑन कर लें।
बीच में किसका नहीं है? अच्छा, एक क्वेश्चन।
जी सर।
थैंक यू सर, हमने स्क्रीनशॉट ले लिए हैं। अब आप लोग लीव कर सकते हैं। मैं मीटिंग बंद कर दे रहा हूँ सर अब।
थैंक यू सर।
Okay, thank you.
थैंक यू मैम।
Thank you, sir.
यहाँ से